What is a gravity dam? A gravity dam is a hydraulic structure which resists all the external forces acting on it by its own self-weight. The forces that act on a gravity dam includes the weight of the dam, water pressure, uplift pressure, earth and silt pressure, ice pressure, wind pressure, thermal, wave and earthquake forces. Now, if the dam has to fail, what will be the reason behind the failure? The reason behind the failure will be these forces, isn't it? So, if a dam is to fail, the reason will be these forces, and you will be knowing all these forces have particular point of application. So, there will be moments developed, right? So, the cause of failure of a dam will be these forces and the moments developed due to these forces. Okay. Now, if the dam is full, the moment will be about the toe point. If the dam is empty, the moment is taken about the heel point. In general, if the dam is full, the forces and the moments will be acting at the toe, and if the dam is empty, it will be acting at the heel. These forces and the moments together or in isolation cause the failure of these dams. Forces and these moments are the cause of failure of these dams. Okay. The dominance of the force will decide due to what mode the failure will happen. Okay. So, the failure can happen either by overturning, or it can happen by sliding, or it can happen by compression, or it can happen by tension. Which type of failure will occur, that will be decided by the prominent force and the most dominant force and the moment because of that force. Okay. So, now we will be seeing the force which causes these kind of failures. Which force causes which kind of failure? First, we will be seeing the failure due to tension cracks. As you all know, the dams are usually made up of gravity dams will be made up of concrete or masonry. Both these materials are good in compression, right? And they are not good at all in tension. So, whenever tension develops, the structure will have cracks. But then, usually, these conditions occur when tension will occur only under severest load condition. So, what you do is, these worst loading condition will just occur momentarily or for a little time. For that reason, you will give a certain permissible tensile strength for high concrete gravity dams that is under worst loading condition, and it is taken as 500 kN per meter square. Okay. Having understood this, we will see how the tension is going to develop in a dam. Okay. You will be knowing these are the forces that act in the dam, right? There are a number of forces acting on the dam. Now you can sum up all these forces into two principal directions, x and y, isn't it? Resolving the forces along the x-axis as well as y-axis. Now, having resolved these forces, now you have two forces which will be acting in the vertical direction and one acting in the horizontal direction. The vertical and horizontal direction forces can be either in vertical direction forces can be either in the upward direction or it can be in the downward direction. The horizontal direction forces can be in the downstream direction or it can be in the upstream direction. Okay. So, you have two possibility for horizontal forces and two possibility in the vertical forces also. Now, in the case of gravity dam, the vertical force usually it happens to be in the downward direction. Okay, because the weight is more, the weight always acts in the downward direction. The vertical force will be acting in the downward direction. Okay, so this is the least possible case in case of a gravity dam. So you can confine our further studies on the downward direction of the vertical force, that sigma V is acting in the downward direction. Now we will see sigma H. the sigma h or the horizontal force. What will be the cause of the horizontal force? The cause of the horizontal force will be the hydrostatic pressure that is acting on the dam. But this hydrostatic pressure comes into play only when the dam is full, isn't it? When the dam is full, the water will be exerting pressure, and that is called as the hydrostatic pressure. Maybe there is some tailwater pressure at this side also, but then the major pressure, major force that comes in the horizontal direction is this hydrostatic pressure that occur when the dam is full. Now, the summation of all the forces in the horizontal direction in the case of dam full will be towards the downstream direction. Okay, when the dam is full, the horizontal, the sigma h will be in the downstream direction. Now, if the dam is empty, then if there is any tailwater, there may not be any tailwater, but if it is there, or if there is some other forces that is acting on the upstream direction, then the horizontal force sigma h can be in the upstream direction also. That is the dam empty condition. Here we are considering the dam full condition, that is water is there in the upstream side. So here you have sigma h that is acting in the downstream direction. Okay. Now this sigma h and sigma v represents all the forces that act on the dam. Okay. Now we can confine our study to two forces, sigma h acting in the downstream direction and sigma v acting in the downward direction. Now let us club these two things also, these two sigma h and sigma v. It can be resolved into a single force, that is the resultant. That is the resultant of sigma h and sigma v. Now all the forces that act on the dam can be represented by this single force, the resultant. Okay. Now this resultant will tell us what is the nature of failure of the dam. The probability of occurrence of this resultant anywhere in the base. If the resultant can occur, see, this is the dam structure. You have the sigma v, sigma h and the resultant r. The resultant most probably will occur somewhere along the base. Can go for the downstream side also, but usually it occurs in the base region. Now, the exact location of the resultant is governed by the dominance of vertical or the horizontal force. Where the R will be, the resultant R will be, where is the location of R? It is decided by either the dominance of H or V. Okay, whichever is a higher force, the resultant will be moving towards that force. Now consider the case when the dam is full. Now if the dam is full, in that case, the R value will be moving from, will be having some value, some direction or location, any of these locations. It will be, most probably it will be in the base in this region, the R value. Okay. Now if the dam is empty, what will be the case? The dam empty case, V will be always acting in downward direction, so no doubt about V. But the value of H, sigma H, the direction of H, it can be in the upstream direction also. If there is any earthquake or if there is any water pressure in the upstream direction, the sigma H will be in the upstream direction. The sigma H can be in the upstream direction. Okay, the sigma H is in the upstream direction. The resultant will now change its direction. The resultant will be somewhere here, or in the previous case it was near the toe. Now the resultant has moved towards the heel of the dam. Okay. For stability analysis, it's actually governed by the condition. If the dam is full or dam is empty, the stability is usually governed by these conditions, that is, dam is full or dam is empty. So it is this condition that decide if the resultant is moving towards the heel or moving towards the toe. And it is the position of this R which decides the mode of failure, that is, if it is tension, if it is compression, or it's overturning, or if it is sliding. It is this R that decides, this resultant that decide the mode of failure. Now let us consider our case, that is tension. How will tension failure occur? Consider the dam full case, this condition. The dam is full. The resultant is inclined towards the toe. When the dam is full, the horizontal and the vertical forces will be like this. H and V will be like this. The resultant will be like this only. It will be somewhere towards the toe. Now, suppose the dam was full now. The initial condition, the dam was full. Now, suppose the water level in the dam is getting reduced. Okay. Now the water level is reducing. What will happen to the sigma H value? The sigma H value will also be reducing. Okay. And in a particular condition, when the dam is empty, what will happen? The sigma H value will become 0. Sigma H will become 0. That is a particular condition. Now, otherwise, the sigma H value will be reducing. The magnitude of sigma H, direction may remain the same, but the magnitude will be reducing. If the magnitude of H is reduced, what will happen to our R value? The R value will be shifting towards the vertical, sigma V. Okay. The resultant is shifting towards the V value, that is the vertical value. Now, when there is no water in the dam, the water level reduced and it reached 0. The water level is now, dam is now empty. The sigma H will become 0. The V value as well as the R value will now coincide, isn't it? Because H is not here, the V and R will now coincide. Both passes through the centroid of the dam. Sigma H and sigma V will now pass through the centroid of the dam. Now, suppose the water level is now increasing. It started raining, now the water level is increasing. When the water level starts increasing, the sigma H value will be also increasing. Okay, for each of the increase in the water level, sigma H will also be increasing. What will happen to the R value? The R will now shift from V. It will be moving, and it will be moving. It will be moving towards the H value. So, from this we can understand that based on the water level, the R value is shifting. It is having a range. It can fluctuate between any of these points. Okay. Now, here comes the middle third rule. As I have already said, it is this R value that decides the mode of failure. The R value as well as its position, its location decides the mode of failure. So, the mode of failure is governed by the middle third rule. Now, what is a middle third rule? Middle third rule says that if a dam will be safe if the resultant is within B by 6. So, I have a dam structure like this. I divide the base. This is the base B. Divide the base into 3 equal parts, that is B by 3, B by 3, B by 3. Now, this is my centroid. Okay. and that comes the central b by 3 part. This central b by 3 part can be further divided into b by 6 plus b by 6. Okay, so this is the center, and here pass the, on either side you have b by 6. Altogether it comes the central b by 3 part. If the resultant pass through this part, this central b by 3 or b by 6 on either side, they both represent the same thing, then the dam is safe. That is what the middle third rule says. Now, let us understand the middle third rule a little bit better. Now, suppose I have the dam structure like this. This is my O value, that is the centroid value. The vertical forces will be acting like this and the horizontal will be acting like this. Now I have my R value. This R value is passing at the base at O dash, and so this O dash will be my eccentricity E value, that is E. O dash, that is the distance between the centroid and the point at which the resultant pass through. That is called as the eccentricity E. Now, there will be stresses developed because of these forces. Now, let us see the forces. What are the forces that comes into play here? You have the vertical force, the resultant, and the horizontal force, isn't it? Now, the direct stress at every point, can see that the direct stress, the contributing factor to the direct stress is sigma V. This sigma V is completely subjected, is causing a compression. So the base of the dam is subjected to compression. In this case, then the dam is full. Here, this condition is that the base is subjected to compression. So, the vertical normal stress at any point of the dam can be obtained by a combination of direct as well as bending stresses. So, we have the direct stress as well as the bending stress due to the resultant. So, total vertical stress that act on the base of the dam can be obtained by sigma V is equal to direct stress plus the bending stress due to the resultant. Now, what is the direct stress here? That is sigma V by A. That is the direct stress. Plus or minus the bending stress. What is the bending stress here? Sigma V by I into E into X. Okay. Now, we will just understand these terms in more detail. What is the sigma V? Sigma V is the vertical stress at the base. What is the stress that comes in the base of the dam? And sigma V is all the forces that act in the vertical direction. A is the area of the base. I is the moment of the inertia of the base as well as X is the distance of the centroid, and E is the eccentricity. Now we will see this equation. We can just rewrite this equation: sigma V by A plus or minus sigma V by I. What is this I value? I will be equal to B cube by 12, isn't it? If you are considering a dam of, for sake of analysis, what you will be doing is, you will be considering a dam of unit length. So, the area will be, this is B and D is equal to 1. So, you can say that I is equal to B d cube by 12, or it can be B cube by 12 in this particular case, into eccentricity into X, right? Now, what will be this equation? You can derive it as sigma V by A 1 plus 12E by B square into X. Now, what is this X value? X will be equal to B by 2. b by 2. Here this is the base value, this is the toe and this is the heel. What is the distance from the centroid? It is b by 2. This is also equal to b by 2. So x is equal to b by 2. So this equation becomes sigma v by a sigma a by, this a is equal to b into 1. This is equal to b into 1 or as b. So a sigma v by b into 1 plus or minus 6e by b. This is the equation. So how you get this equation? This is our base equation, sigma v by a plus sigma v by I into e into x, where sigma v by a is equal to b into 1 considering a unit length, plus or minus sigma v into e by I is equal to b cube by 12 into b by 2. X is equal to b by 2. Reducing this equation, we will get it as sigma v by b into 1 plus or minus 6e by b. Okay, this is the total vertical stress that act on the base of a dam. Okay, now let us see the cases of stress distribution diagram of a dam full case as well as the dam empty. Now in the dam full case, you can see that the horizontal force and the vertical force are acting and there is a resultant. And this resultant will be producing a normal reaction back and it will be at a distance of e, that is the eccentricity, right? Now what will be the different forces, different compression and tension that comes here? The value of compression when the whole thing is in compression, you can see here the resultant is acting towards the toe. What will happen if the resultant is acting towards the toe? The toe area will be in compression, and if the toe area is in compression, what will happen? Obviously it has tendency to tilt towards this direction and this area will be in tension. Okay, so when the resultant is near the toe, compression will come to play near the toe and the other side, which is the heel, will be in tension. So in this stress distribution diagram, you can see that the first condition is E less than b by 6. That is, the eccentricity is less than b by 6. What is this b by 6 value? You have divided the whole base into b by 3, b by 3, b by 3. That is 1/3. Each section is of 1/3. And of these 3 1/3 sections, you just take on either side b by 6 from the centroid. That is the b by 6 value. The eccentricity is within this limit, within this middle 1/3 section. Then we can see that what will be the compression at the toe section. The compression of the toe section will be sigma v by b 1 plus 6e by b. What will be the compression at the heel section? Sigma v by b 1 minus 6e by b. Now, suppose if eccentricity is equal to b by 6, that is, the resultant is passing through the, here you have the resultant. The resultant is passing through this point, that is b by 6. In this case, what will happen? The toe will be in compression here also, but there won't be any compression at the heel point. It will be a critical condition or threshold condition where the complete compression, the toe will be in compression. The failure won't occur, but then it will be a critical condition. In that case, what will be the value of compression here? The toe area will be completely in compression and sigma y here will be equal to 0. This value will be equal to 2 sigma v by b. Now, let us consider the next condition, that is E is greater than B by 6. That is, the resultant is further moving outward. The resultant is moving outward. Otherwise, you can say that the horizontal force is increasing. In that case, the resultant will be moving towards the horizontal force, and the resultant is now beyond the B by 6 value. Now what will happen? The wall of the toe will be in compression. The compression will be very high at this point. In that case, what will happen? This point, that is the heel, it will start to lift, or otherwise it has a tendency to lift, and then a crack will be formed at the heel area. Okay, the heel will be subjected to, the toe will be subjected to tension, the toe will be subjected to compression, and the heel will be subjected to tension. The concrete or masonry being a material not meant for tension, there comes a crack in the dam structure. Okay, this crack will, what will happen when a dam crack is produced? Now, till this point, the whole dam structure that we considered for our design, that is unit length, this was acting as a single unit. Now the crack has formed. Okay, now what will happen? Now it became two parts, or otherwise you can say that the effective area is now reduced. Once the effective area is reduced, what will happen? You know stress. What is stress? Stress is equal to load per unit area, P by A. Now the area has reduced. The P value is a constant, the net force that act is constant, and then the A is reduced. What will happen? Stress will increase. Once the stress increases, again cracks will be formed. Again the cracks will be formed, which will in turn lead to more area reduction, or otherwise effective area is further reduced and the stresses increases. And in the same way it proceeds, and then finally the dam will fail. Okay, so the resultant is moving. In this case, that is reservoir which is full with water. In that case, you can say that the resultant will be passing through the central middle third portion, and then the resultant, if it shift towards the toe, if the resultant shift towards the toe area will be subjected to more and more compression, and the heel area will be subjected to more and more tension. When the compression in this point increases and the tension in this point also increases, and then finally when a tension is developed, when the concrete or mason is subjected to tension, cracks will be formed. Once the cracks are formed, the effective area is reduced. Effective area reduced means stresses will be produced. The stresses will be increased. When the stresses are increased, the more cracks will be formed. When more cracks are formed, again the effective area is reduced. More effective area reduction means again stresses will be increased, and more and more cracks will be formed. In the same way it proceeds till this dam structure fails. Okay, so this is what happened when the dam is full. Now consider the case when dam is empty. When the dam is empty, the horizontal force will be acting in the opposite direction. Otherwise, if there is an earthquake force or some other force that acts in the horizontal direction from the downstream to the upstream, in that case, this H is acting in the upstream direction. Now consider the variation that comes into play for dam empty condition. In dam empty condition, what happens is this area, that is the heel will be under compression. The resultant will be towards the heel. In that case, this part will be in compression. When heel is in compression, toe will be in tension. If the toe is in tension, the cracks will be developed at the toe. And further, if the resultant is shifting more towards the heel, what will happen? More and more tension will come at the toe part, and it will finally crack. When the cracks are formed, the effective area is reduced. Effective area reduced, stresses will be formed, and more stresses will reduction in more cracks. So it's just cycle reaction. First you have a crack, you have tension and compression producing a crack. When the crack form, area is reduced. When area is reduced, stresses will be developed. Stresses will be developed, more and more cracks will be formed, and again the area will be reduced, stresses will be developed, more and more cracks will be formed. In this way, it continues till the dam structure fails. Okay. So here also, whenever the E value is within the B/6 value, both the heel as well as the toe will be in compression. When B/6 is equal to 6, E is equal to B/6, the heel will be in compression and the toe will be having a effective stress is equal to 0. And now when the E value is greater than B/6, otherwise the resultant is moving closer to the heel part, the heel will be in more and more compression and there will be tension developed in the toe region. When tension is developed in the toe region, then cracks will be formed and the area will be reduced. The effective area will be reduced, causing stress, and this stress causes further cracks, and finally the dam will fail. So what is our aim? If the dam is so you can see that tension crack itself does not fail the dam structure. It just leads to the failure of the structure by producing excessive compressive stresses. It's actually a continuous process. It's not just the first crack that caused the failure. This crack is what leads to the more and more development of stresses and then causing the complete failure. Now, here you can see that this value, that is the P max, must be well within the limit so that it doesn't become negative. If the value gets negative, then only the failure will start. For this and this condition, that is B is less than B/6 and E is equal to B/6, there is no tension developed. Right? In the case of dam full or dam empty condition, in case of B less than B/6 and E equal to B/6, there is no tension developed. So in these conditions, the structure is safe. Only in these two conditions the structure is going to fail. So what is our design criteria? You have to make sure that there is no tension developed in the case of the dam, any part of the dam. So for that, what you have to do, the P minimum value must be at most equal to 0. That is, this value must never become negative. That is the main criteria. It must be 0. The maximum value must be equal to 0. Now, what is this P max and P minimum? P max is equal to sigma V by B 1 plus 6E by B. And what is this P minimum? We have already found it before, that is sigma V by B 1 minus 6E by B. That is the P minimum and P max. So this value of P minimum must never turn negative. Okay, if it turns negative, then the structure will fail. So let us find out the value of P minimum. The value of P minimum is equal to sigma V by B 1 minus 6E by B. This must have a value max equal to 0, isn't it? So if this value is equal to 0, then the whole equation becomes equal to 0, or you can say that 1 minus 6E by B must be equal to 0, which in turn says that E is equal to B by 6. Okay, so this is the maximum eccentricity, possible eccentricity, the maximum value of eccentricity that can be permitted on either side of the center is equal to B by 6. That is, the resultant must lie in the middle third portion of the dam. That is the middle third rule. So what is the middle third rule? The resultant of all the forces that act on a dam must come well within the middle third portion of the dam. In that case, the dam will be safe. The gravity dam will be safe. To find that, what you did, you found out the stress distribution diagram. In that, you marked all the tension and compression, all the tension and compressive forces that comes into play, and we found that in the reservoir full condition, or you can found that this value, that is the heel portion, it must not come under compression. To make it within the the heel must not come into tension. The toe is going to be in compression and the heel must not come to tension. To make the value of tension 0, maximum possible value for safety is T is equal to 0. This tension value is equal to 0. To make that, what you did, you found out the equation sigma V by B 1 minus 6E by B, that is the tension value. This must be have a value maximum equal to 0. So you equate sigma V by B 1 plus 6E by B equal to 0, and we will get that E is equal to B by 6. If E is equal to B by 6, that is eccentricity. Eccentricity means from the centroid how much I can move, that is the eccentricity. So if the eccentricity is within B by 6 on either side of the centroid, the structure will be safe. Okay, so we have the structure, divide it into 3, find the centroid, from there B by 3 is a total and B by 6 on either side. If the resultant is within this limit, the structure is going to be safe. That is the middle third rule. Now based on the middle third rule, you can say that a dam structure, when it comes to tension, whenever it comes to tension, this structure is going to fail. So if the failure due to tension cracks is to be avoided, what you have to do, you have to make sure that the resultant is well within the B by 6 limit from the center. That is the tension crack development. Hope you understood how a tension crack developed. The tension crack develops starts from the resultant. See the resultant, position of resultant. If the resultant is near the toe, toe is in compression. Toe is in compression, heel is in tension. Tension in the heel is increased if the toe is in compression. Now what happens? If the toe's compression goes increasing, tension at the heel also goes on increasing, and then a crack will be formed at the heel. This crack will lead to increase in the stress in the structure as the effective area is reduced, and this in turn will lead to more and more cracks. More and more cracks, more and more reduction in effective area, more and more stresses will be developed, and finally the dam will fail. If the dam is empty, the reverse, that is the heel will be in compression. The resultant will be towards the heel. Heel will be in compression, toe will be in tension. When the compression goes on increasing, the tension at the heel, at the toe will also increase, and if it exceeds the permissible limit, crack will be formed at the toe. This crack will reduce the effective area of the structure, and this increases the stresses, and this stresses for more and more cracks, and finally the structure will fail. This is the case of tension cracks. Now we will see the next condition, that is the compression. Compression, these materials that we use for the construction, they have a allowable compressive strength. If the compressive strength that comes at the toe or at the heel that we discussed in the previous in the case of tension, if these compressive forces or compressive stresses that are developed is well within the limit, okay, the compression failure won't occur. Now if the compression exceeds the allowable limits of the material's compressive strength, then these materials will fail. Concrete has certain compressive strength, masonry has certain compressive strength. If the compressive stresses that develop at a point in the dam is beyond the permissible compressive strength of concrete or the permissible compressive strength of masonry, obviously it will fail. that is such a failure, that's a material property basically, that is called as a compressive failure or a crushing failure. The next is overturning failure. What is overturning? First thing to know, such a failure won't usually occur in practical condition as the dam will fail before that by compression itself. Now suppose the case here. Now you have the horizontal as well as the vertical forces, all the forces are acting in the system. These forces will be creating some moments. These moments are of two types, that is stabilizing as well as disturbing. The stabilizing moments will be trying to restore it into the previous, suppose I have the force here, this will be producing an overturning moment. Suppose I have water in the downstream or tailwater is there, this will be producing a moment like this. So this is a overturning moment and this is a stabilizing moment. That is it brings back into the structure into its original position. Now consider the case when the dam is full. When the dam is full, this force is very prominent, and also in this side you have the hydrostatic, the silt, wave and the ice pressures. It will cause the dam to rotate about the toe point. This point, the moment will be formed and it will cause the dam to rotate. Now consider the opposite case when the dam is empty. What will happen? If there is any earthquake that is moving towards the upstream side, along with if there is an uplift and all, in that case what will happen? The dam will start rotating in the about the heel part. Okay, so always there are two kind of forces, that is stabilizing and destabilizing, otherwise disturbing force. The ratio between the resisting moment about the toe to the overturning moment about the toe is called as the factor of safety against overturning. The value of factor of safety must be about 2 or 3. Okay, so what is FOS, the factor of safety against overturning? That is sum of the overturning moments by sum of the resisting moments. The overturning moments can be caused by hydrostatic force, silt pressure, wave and wind pressure, ice pressure. All these can be the contributors to the overturning moment. Okay. Now what will be the resisting moment? The tailwater can be the contributor to resisting moment. The sum of the overturning moments by sum of the resisting moment will give you the factor of safety. This value of factor of safety has to have a value 2 and 3, generally between 2 and 3. Then only you can say that the structure is going to be safe. Okay. Here also we discussed the case where the dam is full and the dam is empty. In the dam full condition, you have all these forces acting in the downstream direction. In the dam empty condition, the worst case is when there is a earthquake occurring and the earthquake waves will be moving towards the horizontal acceleration will be towards the upstream side. The dam will rotate about the heel. In this case also you have to find out the make sure the structure is to be safe means the overturning moment must divided by the resisting moment. If there is dam empty, there won't be any resisting moment in this side. The only overturning moments will be the dam won't be safe. So if it is well within 2 or 3, then the dam is considered to be safe. Okay. So this is the case of overturning failure of a gravity dam. Then as a sliding failure, the major force here is the horizontal forces. Now find out all the external forces that act in the horizontal direction and all the forces that act in the vertical direction. Whenever there is a vertical force, there is a friction developed, and what will be the value of friction developed here? It will be equal to mu into sigma v, mu into normal reaction. So sigma v is the normal reaction here. So mu into sigma v is the resisting force developed. If the sigma h value, and compare sigma h and this sigma v value, if sigma h is less than sigma v, or you can say that mu in sigma h is less than mu into sigma v, or mu into sigma v by sigma h is greater than 1. Sigma h is less than mu into sigma v, or you can say sigma mu into sigma v by sigma h is greater than 1. In that case, it will be safe to sliding. That is, there won't be any sliding. If the resisting force is higher, if the resisting force, that is the resisting force here, mu into sigma v, if the resisting force is higher, in that case the dam will be safe against sliding. So just check the value mu into sigma v by sigma h. That is our factor of safety. If it is greater than 1, you can say that the dam is safe. Usually for low dams, you just check for the friction. But in case of bigger dams, you have to consider the horizontal joints also. You can just say that the mu into sigma v is well within the limit, so the dam is safe. In this case, what you have to do is you have to check the shear strength of the joints also. So the shear friction factor will be equal to, SFF will be equal to mu into sigma v plus b into q by sigma h, where b is the width of the dam and q is the average shear strength at each of these joints. Okay. Now what will be the forces that causes the horizontal force? The horizontal force will be either due to hydrostatic, silt pressure, or wave or wind or ice pressure. All this will be the contributors to sigma h. Now the friction will be the contributor to the opposite force. This will be the two forces here. What will be the value of this force? It will be equal to mu into sigma v, that is friction into coefficient of friction into the normal reaction. Now normal reaction, or otherwise V will be mainly due to the weight and the uplift. The resultant of weight and the uplift will give you the sigma V value. And then mu. Mu is actually a material property again. That is the friction coefficient. So you can say that the compression as well as compression was actually a compressive failure, crushing failure was actually a material property. Sliding failure to some extent is also a material property, because the mu value comes here. Mu is basically based upon the material property. Now, having studied all the modes of failure, now you can check the stability of a dam. How to check the stability of a dam? Stability means the failure must not occur. What are the modes of failure? Overturning, sliding, compression, or by tension. If the dam is safe against overturning, safe against sliding, safe against compressive forces, and safe in tension, then you can say that the dam is going to be stable. That is what we are going to check in case of the stability analysis. Okay, we have to check if the dam is safe for all these modes of failure. So first we studied the modes of failure. Just to revise, what is overturning? The resisting moment and the overturning moments are there. If the resisting moment is less than the overturning moment, then the dam will tilt or it will overturn about the toe. In that case, it's a overturning failure. If you have all the horizontal force and we have all the resisting force, if the horizontal forces are less than the resisting forces, then the dam is safe against sliding. Compression, the compressive stress developed by the material must be well within the allowable compressive strength of the materials. In that case, the dam will be safe for compression. Tension, the tension developed is based upon the position of the resultant. The resultant value will be equal to V by B. Sigma V is equal to V by B plus or minus 1 plus 6E by B. If this value is completely in compression, in that case the structure is going to be safe. To make that happen, you have to have it must satisfy the middle third rule, which says that the resultant must pass through B by 6 on either side of the centroid. These are the modes of failure. So we have to make sure that these things are well within the limit to ensure that the dam is stable. Now, to analyze the dam stability, you have two methods, that is two-dimensional gravity method as well as the three-dimensional method. Here we will be studying the two-dimensional method. In two-dimensional method, it's actually dividing the whole thing into the whole structure of the dam into number of individual units, or you can isolate a typical cross section of the dam of unit width, and then you are studying that unit, that isolated section independently. Okay, now you can if the all the dam structure if it is acting monolithically, in the case, as in the case of very narrow valleys, the dams will be having a transverse joint which are well it will be well grouted. In that case, it cannot be assumed to be as independent unit. So this analysis may not be exactly, may not be correct, completely correct. But then usually when the vertical transverse joints are not that doubted, as in the case of a U-shaped valley, then this analysis will be correct. So there are certain assumptions on which the two-dimensional geometry method is analyzed. First one is that, as the basic condition, the dam is composed of number of independent units, and also second is that no load is transferred to the abutment by the beam action. The foundation, it behaves as a single unit, and the joints are perfect. The material that is used is isotropic and homogeneous. The stresses developed is well within the elastic limit. There is no movement in the foundation. If there are some small holes in the dams, they need not be considered. They just have local effects. In case of stress analysis, these holes will not be considered. They just have local effects. These are the basic assumptions on which these two-dimensional gravity dams are analyzed. So there are two basic methods, that is analytical and graphical method. In the case of analytical method, what you do is you just consider unit length of the dam. That is, you have a dam like this, in the other direction it will be extending some length. So you will be considering just 1 unit length of this dam. And then first step, find out all the vertical forces. Second, find out all the horizontal forces. And then find the lever arm of all these forces. And then determine the moment of these forces about the toe and find out the sigma m value. Now to find out the resultant, first you find sigma x bar is equal to sigma m by sigma v, and then find out the eccentricity. Eccentricity is equal to b by 2 minus x bar. Whatever be the position of the resultant that is given by sigma v by b is equal to x bar, and you check if this x bar is within the b by 6 limit. If it is within the limit, then you can use the formula, that is vertical stress sigma v is equal to sigma v by b 1 plus or minus 6 e by b. This is the formula that is used to find the vertical stress that act in the toe and the heel. Okay, that is how you do it by analytical method. That is two-dimensional analysis by analytical method. Now next is two-dimensional analysis by graphical method. In this case, you have to divide the entire dam section into a number of horizontal sections. At some suitable intervals, particular places where the slope changes, you just draw the lines. That is, here you have the outer middle third line, the inner middle third line, and also the other lines here that represents the lines of resultant forces. If the resultant forces, this is at the outer middle third line, this is the inner middle third line. Once you draw these things, you have to make sure that the resultant line must pass through between these two lines. If the resultant is passing within these two lines, there is no tension developed and the dam will be safe. So this is how you do it using a graphical method. For each section, some of the vertical forces, some of the horizontal forces acting in a particular section are worked out and they are drawn graphically. Okay, and checked whether this line is within the outer middle third line and the inner middle third line. That is how you do it in case of graphical method. So you will just give a quick rewind. First you studied the modes of failure. There were 4 modes of failure. Tension was the first. In case of tension, how you analyzed? Toe and heel you took. Toe in compression, heel will be in tension. Heel in compression, toe will be in tension. Wherever tension comes, there comes a crack, and this crack will reduce the effective area, causing stress to develop. This stress will cause further crack, and then again more and more crack will reduce effective area, and so finally the structure will completely fail. That is a tension failure, tension crack failure. Next is compression. It's a material property basically. If the allowable compressive strength and the developed compressive stresses are within the limits, no problem. If the developed compressive strength and the allowable compressive stress of the material are exceeded, in that case the material will fail. Next is sliding. Sliding is actually basically it can come under a material property itself, because we are just checking this horizontal forces are well within the limit of mu into sigma v, where mu is the friction coefficient of friction of the material. And then the last is overturning. Overturning, you have the overturning and disturbing moments, and you have, it can be either in the heel direction or in the toe direction based on the forces that act. It's basically a force analysis in case of overturning. Okay, it can be with respect to the heel. In case the horizontal forces are more, it can be in the horizontal forces are in the upstream direction, or there's an earthquake, the forces are in the upstream direction. In that case, the overturning can be with respect to the heel part. Now, having understood these modes of failure, now you can check the stability of the dam. You have 2-dimensional and 3-dimensional method. In 2-dimensional method, you have analytical and graphical method. Analytical method, you just check using the equation sigma v is equal to sigma v by b, 1 plus or minus 6e by b. You'll be finding sigma v, sigma h, sigma m, and then you'll be finding the eccentricity and checking if it is well within the limit, that is b by 6 limit, using the middle third rule. In graphical method, what you do, you just draw the outer middle third line and the inner middle third line and check if the resultant is well within this limit. That is the graphical method. Thank you. Hope you understood this part.